5.2 Day 2, two-way tables. The first blank here, when finding probabilities involving two events, a two-way table can display the sample space, which is all possible outcomes, in a way that makes probability calculations easier. So example 1 here is actually from our textbook. It says students in a college statistics class wanted to find out how common it is for young adults to have pierced ears. They recorded data on two variables, gender and whether the student had a pierced ear, for all 178 people in the class. The two-way table below, actually to the right, displays the data. Suppose we choose a student from the class at random. Find the probability that that student, in this case for part A, has pierced ears. So just to shorten things up here, let's define our events. Let's use A and B. So let's say event A, that can be the case that the student is a male, and event B, that can be the case where the student has pierced ears. So for the first part here, we're actually just finding what's the probability of B. What's the probability of a student having pierced ears. Another thing that might help us with our two-way table is let's go ahead and just mark this off into rows and columns. And then for the probability of having pierced ears, the probability of B, well, the total number of people, the total number of young adults, whether male or female, that had pierced ears was 103. So 103 out of the total sample size would be 103 out of 178. And we're actually just going to leave it at that. So we don't want to put this as a decimal. We want to leave this as a fraction because this is actually far more descriptive than using a decimal, right? We know exactly how many people in the sample, 103, had pierced ears, and we know the total number of people in the sample was 178. So let's leave this as a fraction. So you'll find that we do that in probability a lot. We'll just leave it as a fraction. Part B, what's the probability that the student selected is a male and has pierced ears? So there's two conditions that you have to meet. Not just any male, but male and pierced ears. Okay, so probability of A and B happening at the same time. Well, let's look at the intersection of males and pierced ears. So there's a really specific place. We're looking at the intersection of males and pierced ears. So here's males, that's a row. Pierced ears, yes, that's a column. Where do they intersect? Right there at 19. So if I can color code this, there's males, there's pierced ears, so they intersect there at 19. So the probability of randomly selecting a student that is a male and has pierced ears would be 19 out of our total of 178. And the reason I'm color coding like this is I'm showing you how to read a two-way table. You look through the males and the pierced ears, yes, where they intersect, that would be the cell that we're interested in. So 19 out of 178, our total. For example, if I had said female and not pierced ears, you would have looked female, not pierced. Those would have intersected at 4. You would have said 4 out of 178. And then if I can just scroll down here, part C, what's the probability that the student selected is a male or has pierced ears? So all the students that meet this criteria, either a male or has pierced ears. So that's the probability of A or B. So let's consider all the males as well as all the people with pierced ears, whether they're males or females. So the probability that you select a male in general, there's 90 males out of a total of 178. So that'd be 90 out of 178 just for the males. And then the probability you select someone with pierced ears would be a total of, looks like 103 out of 178. Okay, but you'll notice if we actually add these two fractions together, that can't be correct. Because, well, for one reason, if you add 90 plus 103, that'd be 193 out of 178. We would get a probability bigger than 1, and we know that can't happen. Okay, well then what's wrong with this scenario? Well, it turns out that if you just add the probability of males and you just add the probability of pierced ears, there's a group that you would have counted twice, and that would be this group of males with pierced ears. So that 19 number, you would have added that twice by putting it with the 103 and with the 90. So a really simple way to fix that, yes, let's add the males, yes, let's add the pierced ears, but then let's subtract the intersection. So let's subtract that 19 out of 178 so that we only count it once, because right now we're counting it twice. So if we can just go ahead and subtract that intersection, so minus 19 out of 178, so that we only count that 19 group once. If we do it this way, we're obviously doing it wrong because we have a number bigger than 1, and we're counting that group twice. So our final answer here would be 174 out of 178. So that's actually a really important concept for probability, is if you want the probability of A or B, you add up the probability of A plus the probability of B, and then you have to subtract the intersection so you don't count it twice. You only want to count it once. And then the last note on this page, it says we can't use the addition rule for mutually exclusive events unless the events have no outcomes in common. Okay, so what's the mutually exclusive rule? Well, if two events are mutually exclusive, that means they can't happen at the same time. Well, then if I said what's the probability of A or B, you would just tell me the probability of A plus the probability of B. You wouldn't have to subtract out any overlap like we did here, because we know mutually exclusive events don't overlap. But in this case, there was clearly overlap between males and pierced ears, so this one didn't really work. We had to come up with a new formula for the A or B scenario. All right, so what is that formula? General addition. So this will cover mutually exclusive too. It says if A and B are any two events resulting from some chance process, then the probability of A or B is equal to the probability of A plus the probability of B, like we just saw, minus the probability of A and B, so minus their intersection. And then if we can use the probability notation from the formula sheets, that would be the probability of A union B, right? That means the same thing as or, equals the probability of A plus the probability of B minus the probability of A intersection B, right? So this would be the case where we write it with the actual probability notation with union and intersection. So that's the one that you'll see on the AP formula sheet. So they mean the exact same thing, just written in different notation. Remember, U is union, which is the or statement, and this guy, the and statement, would be the intersection. Notice I'd use it for the in intersection. U is union, and then the upside down U, that's the intersection. So that would be for our and statement. And notice how much I'm trying to fit that in with intersection and. So and, that's the one where they both occur at the exact same time. Union means either one or the other occurs, we don't really care which, just as long as one or the other happens. The intersection, the and statement, means they both have to be occurring at the same time. So just so you're aware, that's the formula that you're going to see and the notation that you're going to see on the AP exam formula sheet. So the and, they both happen at the same time. The or, either one can happen. We don't care which. And in this diagram, the sample space that's drawn here with the Venn diagram, this really illustrates the example we just did. So for the union, if I want A or B, right? The yellow circle's A, the blue circle's B. If I want to know what's the probability of either one of those occurring, I got to add up the yellow circle and I got to add up the blue circle, but I don't want to count this little inside piece twice. So I've got to make sure and I subtract the overlap, right? And we did that in the previous example because I don't want to count it twice. All right, and the next part here, the Venn diagrams and probability. These are really going to illustrate for us some of the rules of probability, and we're also going to talk about some of the vocabulary behind probability. The first one, you see event A, that's nice, that circle right there, and then everything else outside of A in the sample space, notice it has A with a C up top here. So that's called A complement, and that's really illustrating all of the stuff that's not in A. So the complement of A, we call that A complement, right? It almost looks like it's to the power of C there. So it has a superscript with a C. That's A complement. That means all the stuff not in A. So all the outcomes that are not in A. That would be the green highlighted piece there. That's A complement. And then what's the next diagram over here trying to illustrate? Well, it looks like we have two events, A and B. S isn't anything special, right? S is just the sample space, total possible outcomes. So we're really concerned with A and B, and apparently there's no overlap. So you could say they're broken apart, you could say they're disjoint, or the other way to say it is they're mutually exclusive events. A and B are mutually exclusive events. They have no overlap. So events that are totally separate. Okay, and then this diagram, the green highlighted piece is what we're interested in. And that's clearly where, if we would have two events A and B that overlapped, that would be the intersection of A and B, the part where they happen at the same time. So I'm going to color code this. I'm going to color it orange. And the orange part here, that's the intersection of A and B. So that's A intersection B, if you use the probability notation. And that's when A and B are occurring at the same time, right? So that's the set of outcomes that happen in both, or their overlap. And then the last diagram here, it looks like A is entirely green and B is entirely green. So that would be the case that we just talked about where it's A or B. So if we have successes in A or B, we don't really care which one. Any of them would be considered a success. So the outcomes in either A or B. Just remember, you don't want to count the overlap twice. So if you add up everything in A and you add up everything in B, you've got to subtract out that overlap so it's not counted twice. So let's go to example 2. It says, who owns a home? What is the relationship between educational achievement and home ownership? A random sample of 500 people who participated in the 2000 census was chosen. Each member of the sample was identified as high school graduate or not, and as a homeowner or not. Overall, 340 were homeowners, 310 were high school graduates, and 221 were both homeowners and high school graduates. Part A says create a two-way table that displays the data. So we can start by comparing high school grads to not high school grads, and then we can have a total column, versus homeowner and not homeowner, and then we can have a total underneath each column. So our column variable, we'll use high school grad and not a high school grad, and then our row variable here, we'll use homeowner versus not homeowner. Okay, so we know we have a total of 500 people in the sample, so that would be our table total. So everything when we get done should add up to 500. All in all, it says there were 340 homeowners, so we can put homeowner total at 340. 310 high school grads, so we can go to high school grad, that total will be 310. 221 would be in the intersection of high school grads and homeowners, so 221 would go here. And then from there we can fill in the two missing blanks that go with our two totals. So 221 out of 340 were high school grads and homeowners, therefore the leftover would be not high school grads and homeowners. And then the same logic applies here. High school grad and not homeowners would be the leftover out of 310. So it looks like we could fill in this blank right here, 310 plus something, gives us 500, so that's got to be 190. And then we can fill in our final two blanks here. The total, not high school grads, and there's 119, so the leftover should be 71, and then the leftover here should be 160. So we can kind of piece together, really like a puzzle, the missing pieces for our two-way table. And then going forward, so we don't have to write all these words out each time we use the probability notation, let's define our events. So how about events G means you're a high school grad, and H means you're a homeowner. So we're going to randomly choose a member of this sample. What's the probability of each scenario? The probability that that member is a high school grad. So just a high school grad. So that would be the probability of G, right? That's what we said is going to be our event high school grad. And then we look, for high school grads, there's 310 out of a total of 500. So just 310 out of 500. And we're going to leave our answer like that. Part C says, what's the probability that that randomly chosen member is a high school grad and owns a home? So we're going to look in the intersection of high school grad and owns a home. So probability of G and H. Or if we use the AP notation, G intersection H. So we look at the intersection of homeowner and high school grad. That would be that 221 number, so 221 out of 500 would be our answer, and we're going to leave it that way also. And then part D says, what's the probability that that randomly chosen member is a high school grad or owns a home? So either one of those will work for us. So that's the probability of G or H. Or if we use our AP notation, that's the probability of G union H. So either one of those would work. So we can do the probability of G, the high school grad, plus the probability of H, the homeowner, and then we subtract out the intersection so we don't count it twice. So we've got 310 out of 500 for the high school grad. We've got 340 out of 500. And then let's subtract the people that would be in both of those groups. So let's subtract that 221 out of 500 so we don't count it twice. Already you would have known that if we added these two numbers up and left that as our answer, we would have a number bigger than 500 on top. So that wouldn't fly. So subtract out the intersection and we should be at 429 out of 500. That's our answer. All right, in example 3, the final example here is about phone usage. It says, according to the National Center for Health Statistics, in December 2012, 60% of U.S. households had a traditional landline telephone. 89% of households had cell phones, and 51% had both. Suppose we randomly selected a household in December 2012. Make a two-way table that displays the sample space for this chance process. All right, so let's start by making a two-way table here. So we can use cell phone and no cell phone as our column variable, and then landline versus no landline as our row variable. And then we can have total column and a total row as well. So the first number I put down here is 0.6. How do I know that? Because it says 60% of households had a traditional landline. So for landline, I know the total would be 0.6. 89% had cell phones, so I can go to cell phone, that total will be 0.89. And 51% had both, so the intersection right here of landline and cell phone would be 0.51. All right, and I know we're using decimals in this case, right? We're using really percentages from the problem. So my total should add up to 100%, or just 1.0. And then from there, we can really fill in all the missing pieces. So for the total column, I know this has to be 0.4, right? The difference between 0.6 and 1.0. I know this has to be 0.11 in this cell. So let's go ahead and fill in all those missing pieces. 0.4, 0.11, This has to be 0.38, 0.09, 0.02. So I can use these pieces of information to fill in the ones that I don't know. And then going forward, let's define our events. L, that'll be landline, and C, that'll be cell phone. So we're going to use that as our shorthand going forward for the rest of this problem. And then part B says construct a Venn diagram to represent the outcomes of this chance process. So Venn diagram, that's the one with the circles in it, and then we're going to draw a big rectangle for the sample space. So let's start with, we have our big rectangle here, that's our sample space, and we have our two circles. This will be landline phones, this will be cell phones, and then definitely there's some people that fall in both of those categories. And really that's where we should start. So we know the intersection of these here, if I can go back just a second here, the intersection, people have cell phones and landlines, that's that 0.51 number. So the first thing I'm going to do is I'm going to put 0.51 in the middle of these. Now here's the biggest mistake I see when I see kids make these. For the L, landline, I have a landline but I don't have a cell phone. Kids really oftentimes want to put, for example, like the 0.6 number. But that wouldn't make sense at all. The total proportion of people with landlines, we said, was 60%. So that was 0.6. We've already taken care of 0.51. So the people that have landlines but no cell phone, that would be this 0.09 number. So that's the one that we need to use. So for this part of the circle, you have a landline but you don't have a cell phone, so that would be 0.09. And then how about cell phone but no landline? So if we look back at our two-way table, cell phone but no landline, that would be the 0.38 number. So 0.38 for cell phone but no landline. And then now everything is done except for what percent of people have neither. They would be, we could write a percentage out here for the people that don't fall underneath the cell phone or they don't fall underneath the landline category either. So what percent have neither? So it's actually a very small number. The only group we haven't represented yet would be this 0.02. You have no cell phone and no landline. So the last number here is 0.02. An easy way to check if we did this correctly, we add up everything in here and it should add to 1. So if you add up every single number in the sample space, right, that's supposed to add to 100% or 1.00. All right, Venn diagram looks good. Part C says find the probability that the household has at least one of the two types of phones. So if you have at least one type, that means you have a landline or you have a cell phone or you could have both. So really we just need to represent all the people in the landline and all the people in the cell phone. So perhaps we could just add up these three probabilities right here and get the answer correct. We could also write it this way. What's the probability that you have landline or a cell phone, right? You have at least one. Landline or cell phone. So that would be the probability you have a landline plus the probability you have a cell phone minus the intersection, so we don't count it twice. So probability you have a landline was 0.6 plus 0.89 minus that intersection, which should give us 0.98. So a shortcut for that would have been, well, since we've already drawn the Venn diagram, what's the probability you have at least one of the two types? Let's just add up the people that have just landlines plus the people that have just cell phones plus the people that have both. And that would have given us the same answer of 0.98. So here's how we could do it algebraically using that addition rule, but since we'd already drawn it out with a Venn diagram, we could have just added up those three numbers and gotten the same answer. Or we could have gone about it another way. There's a really easy shortcut. What's the probability that a household has at least one of the two types of phones? So anytime I see that phrase, at least one, I start to think, well, that'd be 1 minus the probability that you had no phones at all. So another way to get to that 0.98 would have been just do 1 minus that 0.02. So the probability you have at least 1, so you could have 1 or 2 or more. In this case, there's only 2 choices. But the probability you have at least 1 is always going to be 1 minus the probability you have none. So that would have been an easy way to get the answer as well. And so part D says find the probability that the household has neither type of phone. Well, that actually should be pretty easy. The probability that there's neither, we can see that probability right now. So the probability you have neither type of phone, if we write it out, that would be the probability that you're not in L, right? You're in L complement, and the probability that you're not in C. So the only time that we have stuff that's not in L and not in C would be this space outside of it. And we know that that's 0.02. So the probability you have neither type of phone, we can see it in the Venn diagram, we can see it in the two-way table, that would be 0.02. But it's worth going ahead and writing the notation. So you're not in L and you're not in C. So you have to be in this area out here, beyond the 2 circles. All right, and then the last part, find the probability that the household has a cell phone only. A cell phone only, so not a landline, just a cell phone. So that would be the probability you have a cell phone and not a landline. And that's actually really easy to visualize on the Venn diagram here. So the people that have a cell phone and not a landline, that would be, you're in this circle, but you're only in this little crescent moon piece, right? You're not in the intersection. You just have a cell phone, not a landline. So that would have to be that 0.38 number. Okay, then how do we write that using our probability notation? So that would be the probability that you have C and you're not in L. So you're C and L complement. So all the stuff that's inside C but not in L, that would have to be that crescent moon. So right here, if I could just shade it, all the stuff that's in C but not in L, that would have to be this piece right here. So that has to be that 0.38 number. So 0.38, but it's worth visualizing it through the Venn diagram and then using this notation in case you see it going forward. All right, that is all for these notes. I'll see you in class.